Welcome again. We are starting talking about statistical multiplexing and queues. So, as you know very well, our analysis of queuing systems is going to be required to understand the nature of delay in networks. And in such computations, we often need probabilistic bounds. The first bound that we're going to learn in this course, essentially the only bound, to be honest, for this chapter, is the Chernoff bound. You already remember Chebyshev inequality from undergraduate probability, but you may not have heard of the Chernoff bound, have you? Has anyone heard of the Chernoff bound before? Yes, from 531, says Ömer. Okay, that's good. That's good. So Chernoff bound is a stronger bound, and it can be made arbitrarily, I mean not arbitrarily, but it can be made stronger because it has more parameters. If you remember, Markov inequality is based on first order statistics, especially the mean, exactly the mean actually, uses only the mean. Chebyshev inequality uses second order statistics. The Chernoff bound uses the moment generating function. So it uses a lot of information, a lot more information about the underlying random variable. Okay, so here is how it goes. Consider a sequence of independent and identically distributed random variables, xi. They have the same mean as they are identically distributed, and they have a well-defined mean. That's what we will assume. And their mean is mu. Okay. For any constant value x, what is the probability that the sum of n of these random variables exceeds n times x? In other words, what is the probability that the average of these random variables exceeds x? Okay, now clearly the larger the x, the smaller the probability. If you may say, this is a very intuitive. If x is around the mean, this bound is going to be a little more informative. For example, if the random variables are positive values and x is 0, then the bound is useless. Clearly, the probability is 1. But for values of x around the mean, the bound is going to be very useful. And the bound says this probability is upper bounded by this expression. In the exponent, we have negative n times the supremum of this thing, which looks kind of ugly, but let's try to see what it is. It says, okay, I have a parameter theta, okay, which is the parameter of the moment generating function. You remember moment generating functions from your probability courses. For a distribution random variable x1, we compute the moment generating function of x1 by taking the expectation of e to the some parameter theta x1. Sometimes we call this parameter s. It is related to the Laplace transform, right? Expectation of e to the theta x1, where theta is a parameter that we can this will work for any theta. So moment generating function is a function of theta. So what is the purpose of the moment generating function? Basically, it lets us go from the distribution to another domain, just like the Laplace transform takes us from time domain to frequency domain, to S domain, right? This moment generating function changes the domain. Why is it useful? Because essentially it converts I mean, this is very roughly speaking, it converts convolutions to multiplications, etc. So anyway, so in terms of the moment generating function as a function of theta, we have theta x minus log of m of theta, and then we take the supremum of this over theta. Why are we taking the supremum? It would work even if we did not take the supremum. But when we take the supremum, we make the exponent as large and negative as possible. And that would tighten the bound. Okay. Now, in the specific case that the xi's are Bernoulli random variables with parameter mu, which in that case, you know that the mean is mu, okay? And x is between 1 and mu, then the probability that the sum of xi's exceed n times x is upper bounded by the by e to the power minus n times d x mu, the distance between x and mu. What does this distance mean? This is the Kullback-Leibler distance, which we will remember from information theory. Okay, so the Kullback-Leibler distance between two Bernoulli distributions. Remember, the Bernoulli distributions are a Bernoulli random variable takes the value of 1 with a certain probability, takes the value -1 with another probability. I'm sorry, 0 with the other probability. So they are basically two binary distributions. One is p1 minus p, the other is mu1 minus mu, or in this case, x1 minus x. So the Kullback-Leibler distance is given by this expression. And when you compute this expression and put it into the exponents, you find the Chernoff bound. We will now momentarily see a simple application of it.